Have you ever wondered, how does your map pinpoint your location accurately? Of course, it uses GPS, but have you wondered, how does a GPS works? In short, your phone passively listening, it's listening to a chorus of artificial stars. So let's begin our journey to understand how GPS works. But how does simply listening to a satellite tell you where you are? The answer lies in a beautiful, purely geometric problem that starts in 2 dimensions, scales up to 3, and ultimately requires us to solve for a 4th dimension, time. Let's build them. Imagine you are lost on a completely flat, infinite plane. You have no idea what your x and y coordinates are. Suddenly, you receive a signal from a tower at known coordinates. Geometrically, what does this mean? It means your location is restricted to a circle. You could be anywhere on the perimeter of this circle. Now, you pick up a second signal from a different tower. We draw a second circle. The intersection of these 2 circles narrows your possible location down to exactly 2 points. To break the tie, you need a third tower. The third circle intersects at exactly one of those points. You have pinpointed your exact x and y coordinates. This process is called trilateration. But we don't live in a flat 2D world. In our 3-dimensional reality, a set distance from a satellite doesn't give you a circle. It gives you a sphere. If you know your distance from one satellite, you are somewhere on the surface of a giant sphere floating in space. If you slice 2 intersecting spheres, you get a circle. Add a third satellite, and that third sphere slices through the ring, leaving exactly 2 possible points in the entire universe where you could be. Usually, one of these points is absurd, deep in space or inside the Earth's core. The Earth itself acts as a massive 4th sphere, ruling out the impossible answer. So, 3 satellites are all we need for an exact 3D location, right? Theoretically, yes, but practically, we have a massive problem. Up to here, we have been assuming that we know the distance from a satellite, but clearly our smartphone doesn't. So, how does your phone actually know its distance from a satellite? It calculates it using time. The satellite broadcasts a signal moving at the speed of light, stamped with the exact time it was sent. Your phone checks its own clock when the signal arrives to calculate the time delay. But light is incredibly fast. If the internal clock on your phone is off by just 1,000th of a second, your calculated distance will be wrong by 300 kilometers. Satellites use multi-million-dollar atomic clocks, keeping perfect time. But your phone uses a cheap quartz oscillator. Your phone's clock is always wrong. Because your clock is wrong, your calculated distance to every single satellite is distorted by the exact same amount. We call this distorted distance a pseudo-range. Let's call your phone's clock error B. We now have 4 unknown variables, your x, y, and z coordinates, and your clock error B. B is product of speed of light and the error incurred by the clock. So B is constant for all the satellite. You might be thinking, if the error is the exact same for all 3 spheres, why don't we just adjust their radii by the same amount until they intersect at the same point, because building a whole satellite will be much more expensive? Here's the geometric reality. If you only use 3 equations, you have 4 variables. In algebra, an underdetermined system has infinitely many solutions. If you guess a wrong time error B, the equations will simply shift the values of x, y, and z to match your guess. It forces an intersection at a completely incorrect location. Visually, as you adjust B, the intersection of the 3 spheres traces an infinite curve through space. To lock down the one true reality, you need a 4th constraint. You need exactly 4 equations for 4 independent variables. When you pull in a fourth satellite, there is now no longer any mathematical freedom to slide the location around. The system collapses down. There is only one specific value of b that allows all 4 spheres to mathematically kiss at precisely one point. But your phone rarely stops at 4. Modern smartphones routinely track 8, 12, or even 20 plus satellites simultaneously. When you have 6 satellites, your phone sets up 6 equations for the same 4 variables. This is called an overdetermined system. Why do this? 2 reasons. First, error checking. With 5 or more satellites, the phone can perform RAIM, Receiver Autonomous Integrity Monitoring. If one satellite is broadcasting faulty data due to a hardware glitch or atmospheric distortion, its sphere won't align with the others. The phone mathematically detects this outlier and completely discards it. Second, averaging out noise. Radio signals face slight unpredictable delays passing through the ionosphere. By combining data from a dozen satellites, the phone mathematically averages out these tiny errors, shrinking your location accuracy from a 5-meter radius down to centimeters. It's not just how many satellites you have, it's where they are. This brings us to a concept called DOP, dilution of precision. DOP describes how the physical layout of the satellites in the sky changes the size of the error gap. Imagine 4 satellites bunched up directly above your head. Because the satellites are clustered together, their circle boundaries run almost parallel and are very close to each other. A tiny measurement error allows the intersection point to easily slide wildly along the boundaries across a huge distance. Your phone will struggle to find the exact mathematical center, making your GPS location jump around. This is high DOP. Now imagine the satellites are widely scattered. This is strong geometry. Here, the circle boundaries cross at crisp perpendicular angles. Because the boundaries are far apart, where they touch, the exact same tiny error cannot cause the intersection point to slide. It is highly unlikely your location will drift, resulting in a rock-solid location lock. This is low DOP. Solving this massive overdetermined system of nonlinear quadratic equations isn't trivial. The processor in your phone uses numerical methods like least squares or Newton-Raphson iteration. It starts with an educated guess and rapidly iterates, tweaking the numbers until the error approaches 0. It does this multiple times a second. So the next time you look at that blue dot on your map, remember what it took to put it there. You are looking at the solution to an incredible geometry problem involving intersecting spheres, the speed of light, the 4th dimension of time, and the silent, invisible symphony of satellites thousands of miles above your head.